Welcome back, everyone. Today we're going to be looking at a real classic of a guitar pedal, and that is the Boss Blues Driver, the BD-2. And one thing that is really interesting about how they have implemented everything here is through the use of what is called a differential amplifier. And we'll talk about how that works. First, though, this is the schematic for our circuit. It does not have any of the flip-flop bypass switching. This is just the signal path and the power section here. But with that, let's go ahead and jump into it. So when I talk about a differential amplifier, I'm talking about a circuit that amplifies the difference between two circuits. And an op amp is a good example of a differential amplifier if you use both the inverting and non-inverting terminals. However, you can also do it with transistors. And in fact, if we look right here in this section of our circuit, this is a differential amplifier. And in fact, the BD-2 uses two of them. There's another differential amplifier right here. This arrangement of transistors, it makes it so that we amplify the difference between the signal on the, because these are JFETs, on the gate of one transistor and the gate of the other transistor. And we'll talk a little bit about how that works. If you want to learn more about it, though, there are lots of great articles online about differential amplifiers. But the basic principle is this. With a transistor, we typically put the signal, the input signal to the transistor, on either the base for a BJT or on the gate for a FET. But the thing is that the emitter or the source for a FET, the emitter for a BJT or the source for a FET, can actually be used as a second input. Okay, we can actually put a signal in here, and we can it'll end up summing inside of the transistor. But when we do this, there are a couple things that need to be taken into account. The first is that the relationship between the signal on the base and the signal on the emitter is that they are going to look out of phase with each other when we feed a signal in on the emitter. The other thing to keep in mind, or rather the source for this JFET, the other thing to keep in mind is that when we use the source as an input, it has a very low input impedance. A lot of times we use a JFET because it has a very high input impedance on the gate, but on the emitter of a BJT or on the source of a JFET, it has a very low input impedance. And so part of the issue here is that with a really low input impedance, we have to make sure that we can drive this low input impedance sufficiently so that we actually get the differential amplification out. And so that is actually the job of this second transistor here, is to drive a signal onto the source of this JFET so that we then have our two signals here. It amplifies the difference between them, and we take it off of the collector of our JFET. Okay, so still just talking about this differential amplifier, we're just going to take a little bit of a look at how things work. We have the signal that comes in on the gate. It comes out on the collector like this. And in the case of this particular circuit, it now comes to a PNP BJT. So this is important because usually we use NPNs mostly, but PNPs, this is our emitter here, which means we're pulling the signal off the collector, which is going to be out of phase with the signal on the base. And so this signal is then going to be fed this direction. We have a gain pot that determines the overall series resistance here. And so that controls the gain of our differential amplifier. But the signal comes in here onto the gate of this JFET. And because we're tied directly to power here on the collector, and we're driving it from the source, that means that this is essentially a source follower, which has a very high input impedance and a very low output impedance. And it's this very low output impedance that we want so that we can drive the low input impedance on the source of the first JFET. So what that does is it makes it so that we are actually amplifying the difference between the signal here and the signal here. Okay, so that is the basic concept of operation. Now that we understand the basic concept of operation of that differential amplifier, let's look at the specifics of how we're actually using it in this circuit. So from the input, we have a pull-down resistor, we have a DC blocking cap, we have a resistor to a reference voltage, which sets the bias of this first JFET, and it also sets our input impedance. And so the signal comes in here, and now what we're going to do is we're just going to treat the differential amplifier as one block. Okay, so we're going to treat this as one block. So we have an input that comes into the differential amplifier on this first input. We have the signal that comes out. It gets inverted here. It gets fed back over to here so that it's the input on the second terminal of our differential amplifier, so that we are actually driving this differential amplifier with what's called a differential input, meaning that the input here is out of phase with the input here, so that when we amplify the difference between them, we get a really big voltage swing out. Okay, so we get a really big voltage swing coming out on our output here, and we have we've got this resistor and cap off the gate here, which is going to set the bias current of this JFET, and this fixed resistor along with our variable resistor is going to set the DC resistance, and so that's going to actually set how much signal we've got on the gate of this JFET. And when we have very little signal here, then the difference between these two isn't going to be very big, since this is out of phase with this. But as we increase the amplitude of the signal here to the point where it becomes, on the same order as this input but out of phase, we get the very large voltage swing out here. Okay, so our differential amplifier is doing that thing. We've got a little cap here in the negative feedback loop of our transistor to maintain stability at high frequencies. It's very much like putting a small value cap in the negative feedback loop of an op-amp. Transistor R7 is setting the gain of our PNP transistor here. And on the output of this transistor, we now go into this network of passive components. Okay? The cool thing about this network of passive components is that if we were to take our resistors, take this resistor and this resistor and this resistor, and we were to change them for potentiometers and kind of rearrange the drawing a little bit, we would see that this is a classic tone stack, a classic amplifier tone stack topology. Okay, so what they've done is they have created a fixed tone stack in the pedal here. And so it's because they wanted to shape the output in a very specific way. But if you wanted to make a mod to this so that it had a different response, you could either change the value of the resistors, or you could even put in potentiometers so that you can have a full tone stack in it. Um, Now with a differential amplifier and a feedback loop like this, what we end up creating is essentially a rudimentary op amp. So this section here is creating a rudimentary op amp with a negative feedback loop. Okay? Essentially this stuff is in our negative feedback loop of our rudimentary op amp. Now, why would they choose to go this way instead of using an actual op amp? Well, there are a couple reasons that could have led to this. First is that most modern op amps actually have a ton of transistors in them that are set up so that to achieve very clean amplification, very large amplification factors, and just trying to be as high fidelity as possible. They don't engineer any op amps to be a less efficient or a dirty op amp, if you will. They're always trying to make them faster, more energy efficient, cleaner, all those kinds of things. But if you set up a basic op amp kind of like this, what you can do is you can start overdriving the actual op amp itself based on how much gain you put in here. Okay, and that can contribute to some of the clipping characteristics. If you were to just use a regular op amp, you can get a regular op amp to clip, but typically you have to design the circuit specifically so that it'll clip the op amp, and getting the op amp to sound good while clipping takes a little bit of care and design. Now, I can't guarantee that that's why they did it this way, but it is certainly one reason that I can see why they might. So after we have our tone stack here to shape our signal, we now have these diodes set up for hard clipping. Okay, so when you see diodes that are from the signal path to ground or from the signal path to a reference voltage like this, this is hard clipping, where it's just chopping off the top and bottom of the waveform as it gets above either ground or your reference voltage, whatever these things are tied to here. Now, we notice that instead of like the way that it is done in the RAT, where they only have one diode, having two diodes means the signal has to be twice as large in amplitude before it gets clipped. And that can do a couple of things. One, that can be more forgiving with dynamics so that the onset of clipping is a little more gradual. It also can be very useful if the circuitry before it has a ton of gain. Okay, but if you wanted to change the clipping characteristics, the hard clipping characteristics, just change these diodes with whatever you want. You could take out one of the diodes so that it has asymmetrical clipping. You can put in LEDs. You can put in combinations of silicon and germanium or Schottky diodes. Really, any kind of clipping diode arrangement you can put in here. You could even put in, you could tie these guys to a resistor to ground or a potentiometer to ground to get even more fine control of just how much hard clipping you've got, those kinds of things. So that takes care of this top section where we are amplifying the signal quite a lot through our differential amplifier. We're shaping it through a tone stack, and we're clipping it. Now we come down to this bottom section here, and we have a DC blocking cap. We have a bias resistor for our differential amplifier here. And if we just take a look at this section here, you'll notice that the topology of it is exactly the same as the topology up here. Some of the values are a little bit different. But the goal here is the same. The objective here is the same, and that is to have a rudimentary op amp with this differential amplifier and this PNP BJT coming out on the collector. And you'll notice that this dashed line means that the gain pot here and the gain pot here are, it's a dual gain pot, so that as you adjust this one, you're adjusting this at the same time. So you're actually adjusting the gain of these two differential amplifiers at the same time with your gain. And we've got our resistors and capacitors for a little bit of shaping and biasing and everything. We've got a small capacitor for high frequency stability on this BJT, but this is just our differential amplifier block here, okay? And on the output of this differential amplifier block, we then shape the signal some more. This section right here is our tone shaping. Okay, we put, with this resistor and capacitor, we form a low pass filter. And with the resistor and capacitor in parallel, we're also doing a little bit of shaping there. We have a DC blocking cap before we come onto our tone pot. And then we have essentially a variable resistance here that is kind of governing how much capacitance we're seeing between the signal and between ground. So this is working to roll off the high end. As you turn the tone pot up, we're not rolling off nearly as much at the high end because our output is seeing all the resistance into this capacitor, as opposed to when tone is all the way down, it sees no resistance to this capacitor. And so it just serves as a low pass filter. So that's our tone shaping section here. We have our level potentiometer, which is actually just a voltage divider prior to this last op amp stage here. So we have on the output of our volume, we've got this DC blocking cap. We have our bias resistor for the op amp stage. These diodes are just input limiting diodes. They can clip, but they're not going to clip very much because an op amp is always going to try to keep the voltage at all three of its terminals the same. And so if it's the same voltage here and here, these diodes are not going to clip. It's possible, but they're put there mainly as a protection mechanism. The really fascinating thing about this op amp stage here is that what we are creating is a peaking filter, okay? So you notice that we are coming in on the non-inverting terminal. So this is a non-inverting stage. And in the negative feedback loop, we have all of this stuff. Well, this is just a feedback resistor. And this is the feedback capacitor, which means that this guy is going to be setting, this is going to set gain. This is going to do some shaping. But then we have this arrangement of a transistor and some resistors and caps. And what this is actually doing is creating a gyrator or a simulated inductor. If you remember in our parametric EQ video, we talked about how we used op amps to create simulated inductors, but you can do the same thing with a transistor. So this section here is actually a simulated inductor. Okay, it's a simulated inductor that has one end tied to here and the other end to ground. So if we were to redraw this, what it would end up looking like is that from here we would have an inductor. Ooh, that's an ugly inductor. That would go to ground. So from right here, if we're looking at this point here, we would see that we're going through a cap and through an inductor to ground. This creates a resonant filter that is a notch. Okay, so the frequency response of all of this stuff is going to be a notch filter. But because it is in the negative feedback loop, instead of notching it out, instead of notching the response, it's actually going to enhance the response. So the end frequency response of this op-amp stage is actually going to be a peaking filter. And if you look at all the values and you run it all, this center frequency is at between 7 and 800 hertz. Okay, squarely kind of in the upper mid-range of our guitar spectrum. So what we have done then is we've taken our signal and so let's take a look from the very beginning. We've taken our signal, we have run it through this differential amplifier to really boost our signal. We are shaping it through a tone stack. We are clipping the signal through these diodes to ground. We're then amplifying the signal more through another differential amplifier. We're shaping it some more through this tone control and these resistors and caps. We're controlling the volume level. And then we are adding in a fixed peaking filter just before our output. Okay, so there is a lot of frequency shaping going on in here. In a lot of pedals, you'll have, maybe a couple of fixed RC filters, single pole RC filters, and a tone control. But in this circuit, they have gone through a lot of effort to really shape the signal in a specific way with this fixed peaking filter, with the fixed tone stack, and with kind of a more traditional tone shaping setup here. And then there's just an output cap to block DC and a pull down resistor, and it goes to the output. So, if we wanted to break this up in chunks, we have one chunk there, we have this chunk here, we have this chunk here, we have this chunk here, we have this, and we have this. Okay, so this is our first amplification stage, fixed shaping, hard clipping, second amplification stage, passive variable shaping of both level and spectrum, and then a fixed peaking filter to the output. So from just a first look, it looks like a big complicated circuit, and it is certainly much more complicated than your average overdrive. But once we start breaking it down and we recognize that this is just a differential amplifier, then it helps make the circuit much more manageable to kind of interpret what's going on here. So I hope you found that useful. That's all we're going to get into with this one today. If you liked the video, please subscribe so you'll be notified when the next one comes along. And until then, take care. Thanks.